Hi everybody. Today we continue discussion of laws of Newtonian dynamics, that is the laws of classical mechanics. And I will start from consideration of a simple problem Imagine a weight suspended on a thread, and the weight mass is m. And similar thread is tied to this weight here. So these two strings are similar, identical strings. And assume I'm pulling the lower string downward with some force F. I can do it in two different fashions, in two different ways. First, I can pull slowly. And second, I can pull quickly, just in a very quick motion. What will happen in these two different situations? First, I will consider it theoretically, and then I will try to show it experimentally, the same thing. So if I pull down the string, then there will be some forces acting on this weight, on this ball. The first force is F, with which I pull the string. The second force is the weight, which is mg. And certainly the force of tension, which I will denote by T, the force of tension in the upper string. The first question, which is important in this situation, will this ball move, or will it remain at rest? At first sight, it seems that the ball will remain at rest. But actually, any string is stretchable. It can be elongated if we try to pull, if we exert force to elongate the string. It will be elongated a little bit. So if I pull down the string, the ball will shift a little bit downward, because this string is stretchable. It can be elongated like a spring. But a spring will elongate visibly by an appreciable distance, but the string will elongate by a very little distance, so that we may not observe it, we may not be able to observe that little distance of elongation of the spring, or of the string. So it will go down by a very small distance, delta x. If this ball goes down by small distance in some time, then there will be a velocity and there will be an acceleration of this ball. Regardless of the fact that delta x is very small, there will be an acceleration, because that displacement of the ball takes very short time. And in a very short time, very small displacement may produce considerable accelerations. So if there is an acceleration of the ball, no matter how large or how small, we can use the second Newton's law to describe it. And the second Newton's law says that the mass of the ball times acceleration must be equal to a vector sum of all forces acting on the ball. And a force is a measure of interaction. So in order to find all the forces, we have to take into account all the interactions of this ball with the outside world. And there are three major interactions here, which are already shown. That is the gravitational pull to the center of our planet, mg. Then another interaction with the string, and the force of interaction is directed downward, force F. And finally, this ball interacts with the upper string, and the force is directed upward. So the mass of the ball am times its acceleration must be equal to the vector sum of all these forces. If I take this direction as +1 and the acceleration will be positive, then all the forces directed downward will be positive, and that is mg and plus f, and all the vectors directed upward in the opposite direction will be negative. So that will be force T. Now, if I pull the string with force F and slowly increase this force, very slowly, then the ball will be displaced at by some distance. But as the process is very slow, the acceleration will be very, very close to 0. The acceleration will be practically 0 if the force F as a function of time is very slow function, is very, very slowly increasing function. Then the acceleration is 0. Let's show this situation here. This is time, and this is force F as a function of time. So if I increase this force F slowly, then the acceleration is practically 0. And in this case, we obtain from here that the force T equals F plus mg from this expression. If I equate this expression to 0, then I immediately obtain what is the force of tension T. It's equal to F plus mg. It means that T is always larger than F. If this force of friction is larger than F, then the upper string will be the first to break here. The upper string will be the first to break, because the force F is increasing in time, and the force T is always larger than F at any moment of time. So if force T here at the upper string is always larger, then the upper string will break the first. It will break sooner than the lower string, because the strings are identical, absolutely the same string, the same material, the same diameter. Identical strings. And they have identical or similar breaking point. That is the tension which causes the string to break. So if the force F is slowly increasing with time, then the upper string will break. And that is the first situation. The first situation is depicted here when the force F slowly increases with time. And the second situation is when the force F increases very quickly. Very quickly. That is an abrupt function. Very quickly increasing force. Just at some time moment t0, the force increases almost immediately. In this case, acceleration a will not be 0, because the ball will be displaced by a small distance delta x in a very small interval of time. In a very small interval of time. That is, very small interval of time delta t. And therefore, the acceleration will not be 0, the acceleration of this ball. If acceleration is not 0, then we may conclude from the first equation here that the force T equals the same F plus mg minus ma. Now acceleration a cannot be neglected. It may be large. So this is F plus m g minus a. If A is very small, then we obtain the same formula as before, that the tension T equals F plus mg. But if A is large enough, for example, if A equals G, then this round bracket will be 0, and the force T will be equal to force F. In this case, when two forces are equal, are the same, we don't know which string will break the first. Any string may break, maybe the first to break. But if the acceleration is very large, if A is larger than G, then this term becomes negative. And in this case, then the force T will become less than force F. In this case, F will be larger than T, and therefore the lower string will be the first to break. That is the second case here. And the second case is described by this curve. So all this analysis shows that everything depends on how fast the force is changed. If the force is changed slowly, that is the first case, then the upper string will be the first to break. If the force is changed, the force of pull exerted on a lower string, if this force is changed very quickly, then the lower string will be the first to break. That is either the upper string or the lower string, depending on how the force is changing in time. I will attempt to show you this experiment now. So here I have two identical weights which are suspended by identical strings, this one and this one. This is the upper string. And here is the lower string, which is absolutely similar to the upper string. So if I pull the string slowly, the upper string was the first to break. Now I will try to pull the string quickly. That is, the lower string has broken. Exactly in accord with what we have considered here, exactly in compliance with this theoretical consideration. So, a very simple experiment, and intuitively it's obvious that if you pull quickly, then the inertia of this weight will not allow the upper string to break. The inertia will save the upper string, and the lower string will be broken. And the theoretical consideration of this phenomenon is very simple. It's presented here. So, laws of Newton and second Newton's law can explain such an experiment where the body seems to be not moving, it seems to be at rest. And at first sight, it seems to be unnecessary to use the second Newton's law because the body is at rest. But if you consider this situation in a greater detail, you will understand that this body is not actually at rest. It's approximately at rest. But strictly speaking, it must be displaced downward by some small distance if I pull this string downward, because the upper string, as well as the lower string, is stretchable. And the upper string stretchable, it means that it will be elongated as I apply a force to elongate it. As I apply the force downward, as the force F is increased, then the upper string will somewhat elongate a little bit, and therefore the ball will be displaced a little bit. And therefore there will be some acceleration, which may be zero or close to zero if the force F is slowly increasing with time. But the acceleration will not be zero, and it may be even larger than g, larger than the acceleration of free fall, in case the force applied to the lower string changes very quickly in time. So the second Newton's law allows one to analyze this situation. Now I would like to consider an important topic, which is called statics. Again, we can say that if we consider some body of mass m, then mass m times acceleration of this body equals the net force acting on this body. And I will underline that this is a net force. That is the vector sum of all forces acting on the body. In case acceleration is zero, in case the body is at rest, then the net force is zero. And also, if the net force is zero, then the acceleration will be zero and the body will remain in static equilibrium. The body will remain at rest. So the condition for static equilibrium of the body is this one. The total vector sum of external forces acting on the body must be zero. Let's consider a simple example. Let's say be a ball suspended on a thread in this way, and another thread is tied to the wall. And the mass of the ball is m, and this angle is given, it's alpha, and you must calculate the tension forces in both strings. So this string has a tension force, let it be T1, and this string pulls in this direction with tension force T2, and we have to find this T1 and T2 if the mass of the body is known. So the body is at rest, but it's suspended on two threads or on two strings. So the static condition of this body, the fact that it does not move, is due to certain value of these two forces and certain magnitude of these two forces, and we have to find this magnitude. If the direction of the forces is given by the direction of the strings, the first string is horizontal and the second string is directed at angle alpha to the horizontal. Certainly there is another force acting on this ball, that is the gravity pull directed downward. And the condition for static equilibrium is the vector force or net force acting on this body equal to zero. So we must put this condition using our notations in this particular situation. That is vector T1 plus vector T2 plus vector mg. The sum of three vectors must be zero. Why so? Because of the second Newton's law. And we know that the body is at rest, the body under consideration, this ball, does not move. Its velocity is zero, and therefore its acceleration is zero. Therefore, from the second Newton's law, we obtain this requirement that the net force acting on the body must be 0. And from this requirement, from this condition, we may obtain important information about forces. In order to solve the vector equation, we must consider projections of this vector equation on axes. As the problem is the flat, all vectors belong to the same flat surface, then we may introduce just two coordinate axes, for example, axis y and axis x. And this is the origin of coordinate system. And so this vector equation projected on axis x, in projection on axis x, what will it give you? The force T1, now not a vector, but magnitude. Magnitude of this force is just T1, and its projection on x-axis will be negative because it looks in the direction opposite to positive directions. Positive directions are to the right, and all the vectors looking in opposite direction will have negative magnitude. So that is minus T1, then plus vector T2 will have projection equal to magnitude T2 cosine alpha, and vector mg will have its projection on this axis, on horizontal axis, which is 0. Instead of mg, I must write here 0, because the projection of this vector on the horizontal axis is 0. And all this must be equal to 0, this one. That is the projection of vector equation on x-axis. Now, let's consider the projection on y-axis. In this case, vector T1 will have 0 projection. I put it 0 to indicate that T1 is already considered. Vector T2 will have vertical projection, which is positive because it will look upward in the positive direction of y-axis, and it will be positive and equal to T2 sine alpha. The vertical part of vector T2, the vertical part of this vector will be T2 sine alpha. And the vertical part of vector mg will be negative because vector mg looks downward in the direction opposite to positive direction of y-axis. And it will be equal to mg in magnitude minus mg. That is the projection of vector mg on the vertical y-axis. And all this expression must be 0. Why? Because of this fundamental relationship between all the vectors acting on the ball. Now, from these two equations, we have two equations to find two unknown quantities, T1 and T2. We have two unknown quantities which are required in this problem. We must find these two unknown quantities, T1 and T2. And we have two equations to determine these two quantities. Well, the solution is very simple. From the second equation, we can immediately find the T2. Let's do it here. T2 will be equal to mg divided by sine alpha. And if I substitute this expression for vector for the quantity T2 in this equation, then I will easily find T1. T1 will be found as T2 times cosine alpha. So I must multiply this expression by cosine. And that will give me mg cosine alpha divided by sine alpha. And that will be equal to mg cotangent alpha. By definition, sine divided by cosine is tangent. And the reverse quantity is cotangent, right? By definition. So we have found two unknown quantities, T1 and T2, in this problem. How could we find it? Actually, we used the condition for static equilibrium of a rigid body. This condition is necessary because if this condition is violated, then there will be some acceleration, non-zero acceleration. And non-zero acceleration means that the body moves. But in our problem, the problem says that this body does not move. It's in static equilibrium. So its velocity is zero and its acceleration is zero. Therefore, this condition is necessary for static equilibrium. But I would tell you that this condition is not sufficient. It's not sufficient to ensure the static equilibrium. There is another condition which we will study later, and this second condition necessary for static equilibrium is related to rotational motion of a rigid body. We have not yet considered rotational motion. And so when we will consider rotational motion, you will learn another necessary condition for static equilibrium. So finally there will be two conditions. The first one ensures that the center of mass of the body is at rest, and the second one will ensure that the body does not rotate. So today we have considered only a part of conditions, only the first condition for static equilibrium.
Sorry.
Mm-hmm.
I didn't hear when you said about that on the first case for the x-axis, the gravitational force we have put is zero.
Yeah.
Yes, can you please repeat? Sorry.
Yes, this vector will have a zero projection on the horizontal axis because this vector is vertical and the axis is horizontal. So when you project this vector onto the axis, what is projection? For example, you have the axis and you have a point A. What is the projection of this point on the axis X? It's another point which is found as the base of the perpendicular section drawn perpendicularly to this axis. So we find the projection of the end of this vector, and then we find the projection of the beginning of this vector. And if the end of the vector is here and the beginning of vector is here, so that is the beginning of vector B. And so this is A prime and this is B prime projections of vector. If this is the end of the vector and this is the beginning, then the projection of vector will be this one. But in our case, as vector mg is vertical, then points A prime and B prime coincide, and the length of this section will be zero. Therefore, if you have vertical vector, its projected length on horizontal will be zero. That's what we have used here. Instead of mg, we put zero. Another problem from Bukhovtsev. Problem number 88. Two identical weights are suspended from the ends of a string thrown over two pulleys. I will make a drawing. I will make a sketch. Drawing a sketch is very important in most of physical problems, as well as in math problems. So, there are two pulleys and a string which goes over the pulleys. And here we have two identical weights of mass m. And this is also weight, the same mass m. Two identical weights are suspended from the ends of a string thrown over two pulleys. Over what distance will a third weight of the same mass lower if it is attached to the middle of the string? So if here we tie a small portion of string and attach here the same body with similar mass, the same mass, masses of all three bodies are equal. Over what distance will a third weight over what distance will it go? So originally we suspend this weight so that the string is horizontal, and then we allow this weight, we don't hold this weight anymore, we allow it to go down. So it will go down at some distance, and then after some vibrations, after some oscillations here, it will stop in certain position. And these two weights will go up, certainly, will go up at some distance. So we have to find at what distance will this third weight go down. What will be the displacement of this central body? The distance between the axes of the pulleys is given. This distance between the axes is 2L, so that this distance is L, and this distance is also L. The friction in the axis of the pulleys is negligible. No friction here. No friction here. It should be drawn in this way. Yes. No friction here in the axis of this pulley. And the string itself is supposed to be weightless. It's negligible mass. So, after this middle weight goes down at some distance, we will have the same picture, which must be redrawn. So this pulley here, this weight here, this one goes down. Actually, if the distance between the centers of the two pulleys is 2L, it's given, then in order to find the displacement of the body, we have to find this lag in one of the right triangles, which here are shown. So this is the right triangle, and the leg, the vertical leg of this right triangle will be equal to displacement, which I will denote by h. So the displacement of the middle weight will be denoted by h. After it goes down, the string will form an angle. And we have to find this distance h by which the middle weight will go down, this displacement. Any ideas how to solve this problem? Who knows what should be done? Okay. I don't see it on the screen. I will look later. I will look at it later. Okay, so what should be the method of solving this problem? Actually, this weight will finally be at rest after the oscillations have dampened, after everything, after some lapse of time. This weight will be at rest finally. So if it's at rest, then all the forces acting on it, the force of gravity, mg, and the force which is applied here actually, because this is the string, and the forces acting here and here, forces of string tensions, all the forces must somehow balance each other so that this body be at rest. It means that the vector sum of all forces applied to this point must be 0. That is the condition for static equilibrium. The condition for static equilibrium. The vector sum of all forces must be 0. By the way, it means that the force of tension in one string should be equal to the force of tension in another string. Because if we consider the horizontal axis, and if we consider the projection of all the vectors on horizontal, then we will see that this projection of this vector and here another projection of another vector are looking in different directions, and if they are different, then this body will move, but it doesn't move. According to the statement of the problem, this body will be at rest. So these two projections, these two components of the forces of tension, horizontal components, must be equal so that the body doesn't move. And as there is a symmetry in this problem, we have two identical sides. The left-hand side and the right-hand side are identical. No weight is better than the other. This weight has the same rights in this problem as this weight. There is a symmetry. It means that the angles must be equal. This angle and this angle must be the same. Or this angle alpha must be equal to this angle alpha, because of a symmetry in the problem. If one of these angles is larger than another angle, then there will be no symmetry. And one should ask, why no symmetry? Because the problem is symmetrical, so the two angles must be equal. So that forces applied to this point may be shown separately. And if the force of tension in this string, in the left string, is T, then, and this point is at rest, and this weight is also at rest, then the same force of tension will be here in this string, the same force of tension. And this weight is pulled down by gravity forces mg, and if it's at rest, then T should be equal to mg. And also the same consideration holds for the second part of the string. This vector, this force T here also must be equal to mg. And as this weight is at rest, then the force pulling this weight downward and the force pulling it upward, that is the tension force in the upper string, they also must be equal. So this force is also T, and it also equals mg, because this weight is at rest, so the tension force in the upper string must be equal to the gravity pull. Otherwise, this body will move either upward or downward. Okay, 5 minutes interval. Okay, we continue solution of this problem. So the main idea in considering the motion of a body is the second Newton's law. And if the acceleration is 0, then the net force is 0, the total vector sum of all forces acting on this body. This is just the consequence of the second Newton's law. And from the statement of the problem, it's always clear, in most cases, it's clear that the acceleration must be 0, that the body is at rest. So here, for example, it's given that after some oscillations, after oscillations have dampened, the body will be at rest and it will not move, so its acceleration is 0, and therefore all the forces acting on this body must balance each other. What are the forces? The first force is the gravity pull, and the second force is the force of tension in this string. The force of tension is T. It must be equal to mg. Why do we know it? Because of the statement of the problem. The problem says that this body will be at rest, and we need to find its displacement after the oscillations have stopped. So if this body is at rest, then the tension force in this string must be equal to the force of gravity pull, mg. And the same is true for the tension forces in other two strings. And so we have three forces which are the same in magnitude. How should these forces be arranged so that the total sum of these vectors is 0? We can certainly introduce a reference frame x, y, and we can consider projections of all these vectors. If this is alpha and this is alpha, we can consider projections of all these vectors. But from considerations of symmetry, it's clear that this angle must be equal to this angle and must be equal to this angle. From considerations of symmetry, if three identical forces are pulling in different directions, then the sum of these three forces will be 0 only if this is 60, only if this is 120 degrees, and this angle is also 120 degrees, and this is also 120 degrees. So all these three angles are equal, and as the total angle is 360 degrees, then each angle is just 360 degrees divided by 3, which is 120 degrees. And so if this angle is 90 degrees, it's the right angle, then alpha must be equal to 30 degrees. And this is also 30 degrees. And therefore, the vertical component of this force must be T sine alpha. That is this vertical component. And also the vertical component of another vector will be, again, T sine 30 degrees. And alpha is 30 degrees, therefore sine alpha is 0.5, 1/2. Therefore, the vertical component of this vector is T divided by 2. This is T divided by 2. And the same here, T divided by 2. And so that the vertical component of the first vector plus the vertical component of the second vector will be twice this quantity T/2, which will be T. So the vector sum of these two forces, the vector sum of these two forces will be directed upward, and it will be equal T, and it will be balanced by this force, which is also T, and so the vector sum of all three forces will be 0. If this angle is 120 degrees, equal to this angle and equal to this angle, then everything is balanced here. Certainly we can write equations and consider projections of each vector, but I would not like to make all these calculations because they are very simple. It's obvious without any calculations that based on symmetry considerations, these three angles are equal, and therefore each of these angles is 120 degrees, and therefore alpha, this angle, is just 30 degrees, and therefore vertical component is T over 2, and that's it. And this angle, by the way, here this is alpha, and here alpha is something different. It's not good. It's not good to use the same letter to denote two different things. Here alpha is this angle, and here alpha, it must not be alpha. It must be some different angle like beta. Well, so beta will be what? The right angle minus alpha. This is alpha. So the right angle minus alpha, that is 90 degrees minus alpha. And alpha was found to be 30 degrees, so that will be 60 degrees. Beta is 60 degrees. And I need it in order to calculate the displacement h, the vertical displacement. How can I calculate vertical displacement if I know this leg of the right triangle, which is L, which is given in the problem? This section is L, and this angle is beta, 60 degrees. Then I can easily calculate this h, because L divided by h, L divided by h will be tangent of beta. This is angle beta, and the opposite leg divided by the adjacent leg to this angle beta is tangent beta. And so what I need to find is h, and I can find h from here as L divided by tangent beta, and we know what is beta. This is 60 degrees, so tangent of 60 degrees. That's it. I don't remember what is tangent 60 degrees, but I know that tangent is sine divided by cosine. And I remember that cosine of 60 degrees is 1 over 2, and sine of 60 degrees is square root of 3 divided by 2. So 2 will cancel, and the final answer will be L divided by square root of 3. Is it correct? Seems to be correct. So the vertical displacement of the middle body, middle weight here, the vertical displacement h will be given by this formula L divided by square root of 3 if L is just half the distance between the two pulleys. Any question? Any questions? No? Just look at the solution if everything is clear. So, if there are no questions, I will consider another problem. Let's discuss problem 95. Number 95. All these problems are taken from your home assignment. So when we consider the solution here, it will be easier for you to prepare your home assignment. I show you how to analyze each problem, and the similar method of consideration applies to other problems. Because the same laws of physics should be used. You know several laws of physics like Newton's laws, and now you know the condition for static equilibrium. This is a fundamental law of physics, and it should be applied to solve several problems from your home assignment. And another problem is number 95, which reads, a rod not reaching the floor is inserted between two identical boxes. So we have two identical boxes. Each box of mass m, and there is a rod inserted between them, and it does not reach the floor. It does not touch the floor. A horizontal F is applied to the upper end of the rod. So to the upper end of the rod, force F, horizontal force F is applied. Which of the boxes will move first? Which of the boxes will move first? So this will be box number 1, and that will be box number 2. Which of the boxes will move first? If we pull the rod, the upper end of the rod, in this way, rightward, which box will move first? Box number 1 will move, or box number 2? If they are identical and the coefficient of friction is the same, certainly. Well, I will show you the experimental realization of this problem. So here we have two bars and the rod, which will be just a ruler. So if I push the rod here to the left, my left, then this bar moves. If I push the rod in the opposite direction, then this one moves. You will see that whenever you push the upper end in one or another direction, which block will move? The one to which I exert the force. This one moves. And here, if I exert the force from here, another one moves. Why so? How can you explain it? Based on the laws of physics. So in this particular case, block number 2 must be the first to move. Why? Explanation. Very simple problem, and you must be able to explain it. So when I pull the rod sideways to the right, the upper end of the rod, then the rod will interact in this point with block 2, and the opposite end of the rod will interact with block 1. When we have two forces of interaction, according to Newton's third law, these two forces are equal in magnitude and oppositely directed. So if the rod exerts some force on the block, then the same force, equal in magnitude and oppositely directed, is applied to the end of this rod. Let's denote it by F1. And the same here, if this point of the rod is acting on block 2, then similar force acts on this point of the rod. It's equal and oppositely directed, and I will denote it by F2. So these two forces are equal, and these two forces are equal. They are applied to different bodies. Force F1 is applied to the rod, and minus F1 is applied to block 1. According to Newton's third law, these two forces are applied to two different bodies, and the forces are equal in magnitude and opposite in direction. Everything is very simple. When we pull the upper end of the rod, when we apply force F, we first apply small force and then larger and larger force until the block, one of the blocks moves, until there is a motion. But when the blocks don't move in the beginning, when I just started exerting this small force, and then until the force is large enough, the rod is at rest. It doesn't move, and the blocks are at rest in the beginning. So the conditions for static equilibrium must apply to the rod. Originally, in the beginning, it does not move. So static equilibrium, it means that all the forces acting on the rod must balance each other. Which forces act here? In the positive direction to the right, we have force F, another force F1 acting in positive direction, and force F2 acts in opposite direction. And all these forces must cancel each other. They must produce 0, because originally the rod is at rest. It does not move. That is the condition for static equilibrium of the vertical rod. So, which forces act on the rod to the right? Which forces act to the right? F plus F1. And which forces act to the left? F2. So I may derive from this equation that F2 equals F1 plus F. From the first equation, we derive this relationship between forces. F2 equals F1 plus F. It means that from here we conclude that F2 is always larger than F1. The force F2 is always larger than F1 because F2 equals F1 plus something. So F2 is larger than F1, certainly. And therefore, this force is always larger than this force. The force acting on the second block is larger than the force acting on the first block. If I apply the force F to the upper end of the rod in this direction, to the right of you, then the force F2 will be larger. So this force will be larger. And as the two blocks, block 1 and block 2, are absolutely identical, and forces of friction are identical, equal here, then which block will move first? Where the force is larger. The force exerted to the second block is larger than the force acting on the first block. Therefore, the second block will be the first to move if I increase the force F. This one will move because of this condition, because of this result. So, what laws of physics do we use to solve this problem? First, condition for static equilibrium. Which body is in static equilibrium? The vertical rod. It's in static equilibrium until one of the bodies moves. One of the blocks moves. Until this block moves, the rod is in static equilibrium. It doesn't move. So we use the condition for static equilibrium of the vertical rod. And from this condition, we derive that the force acting on the second block is always larger than the force acting on the first block. It means that the second block will be the first to start its motion. It will be the first to move. And you have observed it. Also, I can choose different orientation of the rod. Originally, I have shown you this. This experiment when the ruler was vertical, but I can keep it horizontal, and the same will hold. The same result will be obtained if I exert the force in this direction. Then this block moves. If I exert the force in different direction, then this one moves. That's it. And the analysis is very simple. Just two simple formulas. The first one is the condition for static equilibrium of the vertical rod. And the second one is based on the Newton's third law, that this force is equal to this force in magnitude. Also, these two forces are equal in magnitude. So nothing more than the condition for static equilibrium and the Newton's third law. There is nothing more to this problem. Any questions? If you have no questions, then we go further. And the next topic I would like to discuss will be a law of conservation of momentum, a very important thing in physics, law of conservation of momentum. So again, I consider a particle or a body of mass m, and if the body is accelerated, then there must be a force acting on it. I will use vector notation. What is acceleration? By definition, acceleration is the rate of change of velocity. So this is m, and the velocity is v, delta v, divided by the time interval during which the velocity changed by delta v. That is the acceleration by definition. Acceleration a by definition equals delta v divided by delta t. And what is delta v? Delta v is some final velocity minus initial velocity. That is the change of velocity during time interval delta t. The change of velocity. Multiplying this equation by delta t, I will find delta t here, so that this equation will be written as f delta t equals m velocity final minus m velocity initial. I multiplied this equation by delta t. So delta t vanishes here and appears here, F times delta T. This physical quantity is very important. It's called impulse of a force. Impulse of a force, or simply impulse. And this quantity is also very important. It's called momentum. Momentum of particle m, momentum of body m. Momentum is usually denoted by letter P. So this will be final momentum, vector of final momentum, mass times velocity final, and that will be the initial momentum, mass times the initial velocity, initial momentum. Of a single particle. All this applies to a single body of mass m. Now imagine we have not a single particle but two different particles, one of mass m1 and another particle, another body of mass m2. And suppose these two bodies, these two particles somehow interact with each other. Somehow interact. Well, suppose they are attracted to one another. Here we have force F1, and this is force minus F1. According to 3rd Newton's law, the two forces are equal in magnitude and oppositely directed. So if this force is F1, then this force is minus F1. I immediately use the Newton's 3rd law. So we can write the same equation for the first particle and similar equation for the second particle. So force F1 acting on the first particle times delta t, some short time interval, equals the final momentum of the first particle minus initial momentum of the second particle. Oh, sorry. Initial momentum again of the first particle. And the same equation, the same consideration is true for the second particle. F2 exerted to the second particle, the force F2 acting on the second particle will be equal the final momentum of the second particle minus initial momentum of the second particle. All this is just a consequence of the 2nd Newton's law. Adding these two equations, we will obtain F1 plus F2 delta t equals final momentum of the first particle plus final momentum of the second particle. These two terms minus, I will put it in round brackets, minus initial momentum of the first particle and initial momentum of the second particle. I will put it in this way. Because minus P1 minus P2, I'm adding these two terms. I can write it down like this, minus and in round brackets. F2 is equal to minus F1 due to Newton's 3rd law. So this term will be 0. F2 is equal to F1 and oppositely directed. Therefore, the sum of these two vectors will be 0. Because F2 equals minus F1. If you put minus F1 here, you will find it 0. And this term is called the final momentum of the system of two particles. because this is not the momentum of a single particle. This is the vector sum of two momenta for two particles, particle number 1 and particle number 2. We have two different particles here. So this is final momentum of the system of two particles. And this is final momentum of the system, initial momentum of the system of two particles. So we may put it like this: a total momentum, final momentum of the system of two particles minus initial momentum of the system of two particles, where large P is just momentum of the first particle plus momentum of the second particle. It's the vector sum of two momenta of two particles. That is the momentum of two particles. This is the change in momentum, equals what? 0. Otherwise, the final momentum equals the initial momentum of the system of two particles. Either way, it's the same. Either you say that change in momentum is 0, or final momentum equals the initial momentum for the system of two particles. If I consider more than two particles, like another particle number 3, particle number 4, number 5, etc. If I have more than two particles, what will change here? We will have to consider forces of interaction between each two particles. And all the forces of interaction between this particle and this, for example, will obey this third Newton's law. And so when you find the vector sum of all the forces, you will, in the same way, obtain 0 due to the third Newton's law, even if we have many particles. And so the same relationship will be true for momentum. The change of momentum of the system of particles will be 0, or the final momentum of the system of particles will be equal to the initial momentum. But the momentum does not change. That is the law of momentum conservation. Law of momentum conservation. Law of momentum conservation. This is the law of momentum conservation. We say momentum is conserved because it does not change. Within some short period of time, the momentum does not change. What about a longer period of time? Well, let's consider this situation. That is the total momentum of two particles, the magnitude of total momentum, and in some short time interval delta t1, the total momentum initially was this one, and finally it was the same. Initial and final momentum is the same. Okay, let's consider another time interval. Again, initial and final momentum will be the same. And if we consider many short time intervals, then we will find that within a longer time interval, not exactly the short time, but a long time interval, the initial momentum will be equal to the final momentum. But these two many time intervals, different time intervals, have different properties because the force of interaction may change in time. Because particles may move and the distance between particles changes, and so the force of interaction changes, be it a gravitational force of attraction or an electrostatic interaction between particles. Such forces of interaction depend on the distance between particles, and if particles move, the distance changes, and therefore the force changes in time. So in different time moments, the forces of interaction are different. But regardless of changing forces, the total momentum of the system of particles remains constant. The total momentum of the system of particles remains constant. And the momentum is conserved, even if forces change. Even if forces change in such a way that we don't know how do they change. We may have no information about forces. The forces may be too complicated. We may have no information about forces. It doesn't matter. The vector sum of all forces will be zero due to Newton's third law. So even if we know nothing about the forces of interaction, even in this case, we know that the Newton's third law applies, and therefore the momentum should be conserved and the law of conservation of momentum should hold for a system of particles. Now tell me, is this law a universal law? Is it applied always? Is it always true? Is it always correct? Can you imagine a situation when this law will be violated? Can you tell me when this law may be violated? Huh? Any ideas? Why? Let the time become longer. We have more and more time intervals here. Nothing changes. The same will hold, the same will be true, the same consideration and the same result will be true. No. The time may go to infinity. The momentum must be conserved. Is this a universal law which is always applicable? Can you apply this law in any situation? Or there is probably some situation when this law doesn't work, when it's violated. Well, look at the derivation of this law. We considered only the forces of interaction between the two particles, internal forces in the system of two particles. Or you may consider internal forces in the system of three particles, or four, or many more particles. But we must consider only the internal forces of interaction so that the Newton's third law will balance all the forces so that the vector sum of all forces will be zero. So if there are only internal forces of interaction, then the law of conservation holds. But if there is some external force acting on any particle, for example, on this particle, I will pull it myself with some other force, external force. Then this force will not be balanced here. So the law of conservation of momentum holds only when there are no external forces acting on the system of particles. And such a system of particles, when no external forces are present, such a system of particles is called a closed system. Closed system means that it does not interact with the outside world. It interacts only internally. The particles interact only between each other, and no external forces are applied here. So the law of conservation of momentum holds only for closed systems of particles, closed systems of bodies. If the system of bodies is not closed, if it's open to external interactions with other bodies, then there will be no law of conservation of momentum. Forget about it if there are external forces. That's it. The end of this lecture. Thank you.